Nice.
Okay, so let's start with the last talk of today by Alessandro Georgoudis, and he will tell us about Hexagon, QSC, and the bottom bridge.
So I would like to thank the organizer for inviting me to speak at this very nice meeting where I'm learning a lot of new things that I didn't know about. As it will be clear, I'm from the high energy integrability community, more precisely about this N=4 Superunion Mills community. So the title of my talk is a bit confusing because I'm using very technical words, but I hope that by the end of the talk, you will understand what we try to do and why this could be an interesting thing. Okay, so this is work in progress still, so we're finishing it up, and this is with Benjamin, which is in the audience, and Arthur, which is a PhD student at ENS. Okay, let me try and give a bit of summary of what I'll try to do, hopefully. So first I will try to show you what hexagons are and why we care about hexagons and how we can use them for computing structure constants. No worry if you don't know what a structure constant is, I will try to explain it. And then I will try to show that there is some very nasty things happening, which probably you know about, which is finite size effects. So these things when you try to compute spin chains or other objects that are not infinitely big, you always get this wrapping corrections. And these are, as you may know, these are very difficult to control. There is some formalism for solving the spectrum problem that allows you to take care of this, and I will try to introduce it briefly, show a bit of history of what happened, and then we'll try to see how this formalism, which is called the quantum spectral curve, though there is no curve, so it can be used to control these wrapping effects. And then I will try to explain the hexagon formalism, and then I will try to focus on a particular contribution of this hexagon formalism, which is called the bottom bridge, and it will be clear why it's called the bottom bridge. And I will try to show how we managed to practically control this wrapping inside this bottom bridge. Okay, let me look at an overview, which is more or less what I said. So I'll try to introduce a bit N=4 Superunion Mills as best as I can. A bit of this quantum spectral formalism for N=4. It's a very technical thing, but I'll try to explain more or less what are the cool things about it. Then I'll try to show you exactly how hexagon work, how this wrapping come about, and then some conjecture that we made with Benjamin and Arthur on how to resolve some problems with this wrapping. I will show some then results very briefly. I will not show any computation, just that we can match objects at the very high order in perturbation theory. So when we talk about loops, we really meant that order of precision that you can go to in the perturbation theory, and how we obtained this from two sides. So first we did a very complicated perturbative computation, and then we were able to match all this information coming from the quantum spectral curve. So practically some dressed integrand with quantum spectral object. And then I'll go to some conclusion, say that we have more results than what I'm trying to present, but I hope this will be enough to fill in an hour. Okay, let me start by explaining a bit N=4. So N=4 is 4D interacting CFT, so it's a conformal field theory. We have conformal invariance, and it is composed of different fields. They all transform in this adjoint representation of SUN. So SUN is this symmetry, is this gauge symmetry of my QFT, and N=4 just means that I have the maximal amount supersymmetry allowed for gauge vector boson, and my field content is exactly this. I have one gauge vector boson, 6 scalars, and then 4 fermions and 4 antifermions, how you want to call them, for a hat. And all this, it's my QFT that I care about. This is a very nice theory. It's conformal also at the quantum level. So if you try and compute the beta function, which is practically this is 0, is control, everything is nice. And it's still a very interesting theory, though it is easy to, well, easy between inverted comma to study. It is part of this big object of study, which is ADS-CFT. It is actually dual to some type 2B string theory on this background. I think if you heard Charlotte talk, this is could be familiar. And what we are interested in on this theory, it's exactly its planar limit. So we want to take the rank of this SUN group to be infinite. We also rescale the coupling of this theory accordingly. And then we end up on this planar limit of n = 4. And it has been shown that this is an integrable theory, so we can use all the cool ideas from integrability. It is just for you to know that actually supersymmetry of conformal invariance combine together to give you this huge group, which is PSU2,2/4. And this is practically the key to why n = 4 is so easy, because this group constrains all the possible objects that I can build very strongly. This was actually used by Bizert and all to bootstrap the S matrix of this integrable theory and other objects. Okay, if this is clear, this is the last you will hear about gauge theory. The rest is hopefully only integrability. There is another thing that actually I need to explain a bit, is that why, what is this CFT and what does it mean to be a CFT? Well, to be a CFT, it practically means that you only need to care about two objects of your theory. So you need to care about multiple correlation function, you don't need to care about complicated things, you just care about this anomalous dimensions and this structure constants. And why is so? No, my internet connection is unstable, okay. Why so? Well, because practically this, the object that you care about to put all your operator into little boxes is the dimension and the spin and other quantum numbers. But most importantly, the dimension for some operators or for some objects of your interest can get quantum corrections. And so these quantum corrections are all characterized by these anomalous dimensions. And the other object that is important are this structure constant. And these structure constants come into play because since this is a conformal field theory, we have an extra important object, which is this operator product expansion, which practically tells you that your operator satisfies some algebra. And if you have two operators, you can practically approximate them as an infinite series of some particular set, which are called primaries. It's not important to know, but you can practically approximate them by knowing the structure constant of your theory. So the structure constant are by itself 3-point functions. So once I have this notion and the notion of the anomalous dimension, which come into the function that dress your OPE, you practically can take whatever combination of operator in a correlation function and then just do OPEs, 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 and then you get infinite sum of objects that you know, so you have practically control over everything, okay? I hope this is clear. Supersymmetry allows you to have special operators which are protected, so in some sense they don't get any quantum correction, so their anomalous dimension is 0. Their bare dimension is exactly what you see. And these are operators that are important to us because in what we will play later, this will be some sort of the vacuum of our integrable picture. Okay. If this is clear or known, I can go on. And exactly what we care about in n = 4, in this integrable limit, or in this planar limit, is only single trace operators. And why do we care only about single trace operator? Well, you can think about it because practically if you, well, in gauge theory, whenever you have some sort of interaction perturbative, you need to dress your diagram by some SUN matrices. This SUN is when contracted together will quantities, and you'll see that the single trace operators are the one that scale survive this end. So these are the things that we care about, and luckily enough, these are the easier piece to study. You can also have double trace, triple trace operator, but as I said, these are suppressed. And what is inside this trace is practically fields plus derivative of what is in n = 4. Okay, the idea that was brought out in 2002 by Minahan and Zarembo was practically, oh, this trace of operator looks very similar to some spin chain. let me try and see if this is true. Well, this turned out to be true and to be the basis for the integrability in n equal 4. And the idea was actually to so study the dilaton operator, which is practically what gives you the anomalous dimension or the dimension of your operator. This can be mapped to the Hamiltonian of your spin chain, so how the spin chain interacts. And then the eigenvalues of this, so the energy of your spin chain is exactly the anomalous dimension. So practically, that's why we never, I mean, if you do integrability in this business, you can also forget about the gauge theory, because at the end, what you care about is an integrable spin chain with PSU 2,2/4 symmetry, and then you just care about finding its energy, and then you know that the energy or the spectrum of your spin chain will be exactly mapped to your anomalous dimension. So the idea is that there is a map between what sort of operators I can have here to special to this spin chain. And this is all very well understood. As I said, non-protected operators, which is what we will care about, can have anomalous dimensions, so can have, and protected operator cannot. And this is, you can understand it as for the fact that, well, I mean, usually you choose this, this particular combination, in this case, Z, as your vacuum. So in some sort of sense, you argue you need to choose a vacuum for your excitation to be put in, and you choose, for example, the vacuum as this ZL, and it is an understanding from the gauge theory that these are half BPS operator. If you know what they are, perfect. If not, it's not super important. But the idea is that these are operators that are protected, that are very nice, and they don't get any quantum correction. Their 3-point function don't get any quantum correction. So this is like a good object to have as a basis, so as a vacuum of your spin chain, and then you insert whatever. It can be derivative, it can be other fields, and this will be excitation in this spin chain picture. Okay. If this is clear, so the idea that we can forget about the gauge theory, we only care about spin chains, then we can try and, oh, this did not move. Why? Ah, okay, I need to use this. Okay, so as I mentioned at the beginning, what can we do? Well, the first thing that was done was actually trying to study very large spin chains. Those are nicer objects. Those were solved and found their spectrums at an anomalous dimension. But then the question came, how can we study spin chains that are small? So for example, something that can be trace of two derivatives with Z2. And these are filled with this finite size correction that pictorially you can imagine as the spin chain living on this cylinder. So these are one end of the cylinder, one end, and wrapping correction are exactly like particles going around this. And as you may know, I mean, these are complicated objects, and the solution was actually found by discovering this, by generating this, what is called a mirror theory, and then writing the TBA for n equal 4. And this, as you may know, is a complicated set of nested integral equations that cannot be solved explicitly, they can only be solved numerically. But this gave the first insight in what are the anomalous dimension at each power of your coupling lambda. So this was a very big step. And then this was transformed by several passages in history. Practically, you can take the TBA, rewrite it as something which is called a Y system. I mean, I don't know if these are also known in the canonical integrable background. But anyway, this Y system then has been shown that is exactly the same as this practically T system that is where you have like Hirota equation, so you can fuse T matrices, and then you have these infinite lattices where you can move around. And these two are practically the same. It's just a rewriting, and for a specific boundary condition, the two are actually, you can actually choose the same starting point for these two. But the interesting piece was actually the introduction of this quantum spectral curve, which is a way of using the analytical structure of this of your T matrices to generate some simpler function, which are called Q functions, and these are the building blocks of then this T matrices. So this is the last step, and this is what we care about, because as in everything, I have way more control into this propping effects. But the idea is that this QSC is like a simple set of equation. It is complicated to solve, but it's a simple set of equation that can be understood, and then can be used to practically solve iteratively for yeah, for finding the anomalous dimension of this n=4 operators. Okay, let me show you a bit of this QSC. As I said, is a non-perturbative approach to compute this anomalous dimension. And the idea is just that, okay, historically it came about because, as I said, from the T system, they noticed that this T function needed to have some specific analytical properties, and then they found that they could rewrite all this T system by using only some very reduced number of functions, which are called this Q function. Some have a name which is P, some are Q. This is some historical fact. And these two Q functions have some specific analytical properties. That is the only information that you need to have, which is they have this P function, they have a very short cut on their defining sheet, and this Q function have two long cuts. This is the only information that you need, and the other thing that you need to know is that how can I choose different Q function depending on which state I want to study, so depending on which spin chain. Practically, all the information is encoded into the asymptotics. So this P and Q function will depend, this is the U space. So this is the space of your spectral parameter. And if you take this limit for U that goes to infinity, so if you look at this very far, far away on the side, you'll know that this P and Q function will scale at some combination of your quantum numbers. So the idea is that you can plug in when you try to solve and obtain this Q function, is that you plug in the information about your state for U at infinity, and then use a lot of these properties and difference equation to construct these P and Qs. Particularly what you use is that is usually analytic continuation. So you analytically continue around this cut, and then you know that this should go into some specific form. And you can use this consistency condition to build up to construct this P and Q. This works both at the perturbative level, so if I want, I can just expand in some series with respect to my coupling, or I can actually solve them numerically and find the value of my anomalous dimension at whatever value of the coupling. I mean, I'm simplifying a lot, there is a lot of numerics behind it, but the idea is this. The idea is that this is we have shifted the problem from trying to diagonalize on a Hamiltonian and try to find or computing Feynman diagrams to practically give me whatever state you want. I can build this P and Q function and then construct with some constraint, and extract the anomalous dimension. I mean, I'm saying a lot of words, but the idea is that this is as we have heard during these days, this is a Riemann-Hilbert problem plus some difference equation that I will show you.
Excuse me.
Yeah.
I'm wondering. So, in a sense, that these zeros of these Q functions just better roots, right?
Yeah, exactly. The zeros of Q functions are better roots.
Yeah, and basically, so it should be just some polynomials.
Yeah, exactly. So this, I mean, at the perturbative level, these are polynomials, and at the non-perturbative level, these are a combination of Zukowskis, which are a particular choice of your, function.
But then on what level there should be this? I mean, this branch cut is this choice, because in principle you can choose different choices of branch cuts.
Yeah, so they've seen.
But does it affect like the physical?
So this is the natural choice. So because I mean, you can see it in two different ways. I mean, you can also see it because you can You can see it from the T matrices, so you can compute the discontinuity of the T matrices and see that it's like a square root discontinuity, and then you know that the Zukowskis has the correct discontinuity, so you argue that these are the correct function for your basis. Or since we have ADS-CFT, which allows you to study the classical limit of this, so the strong coupling limit of n=4 is connected to the classical limit of this string theory, and then from there you see that this integrability in that regime show you that you need to have the square root, root branch cut.
But this is before sending the system to infinity or after?
Yeah, no. I mean, this is the classical limit. Yeah, this.
Yeah. So basically, this branch cuts in principle is where all the beta roots condensate on, or is it?
No.
Or maybe it's something else.
I mean, I don't know if Niklas wanted. Yeah.
If you want to have a beta equation or a spin chain, you would probably be at. So if you want to have a beta equation or a spin chain, you would probably be at G = 0. G is an additional parameter which is a coupling constant which governs sort of the interactions of the spins. But for G equals 0, it's a spin chain, and then you can see that these branch cuts go away, and are probably, these functions are just the P and Q, the Q functions of beta equations. But things become interesting when G is not equal to 0.
Yeah. So yeah, the basis of in this weak coupling limit where you have poles, or where you have, as you said, polynomials, and then you have this polygamma function. This is another basis, and you have zetas, and you have a periodic function. So there's a plethora of function, but it's like contained. So you know what they are, and these two different regimes give you two different approaches. But what I want to say is that you can see it from the classical limit of n. So from the stringy classical limit of n equal 4, you can also see that there has to be this square root discontinuity. So it's there, and you know this. You know, as I said, how to build these T matrices and all these analytical properties, plus some finite difference equations that are these ones, which they call QQ relation, and then you're able to practically construct these Q functions. Okay, let me just say that P and Q actually are related, but you can also have P up and P down, so you can exchange the Q down for the P up. And the important bit that I would like to, anyway, the important bit is this, which is this difference equation that tells you that this P and Q are related with this two index Q function. Anyway, simply put, you have two different system, which is the P mu system or the Q omega system, and you can interchange between them by using this Q. And you can solve only in here, or you can solve only in here, and they will both give you the anomalous dimension at the perturbative level. If you want to do things non-perturbatively, you need to use some condition from both. But this is a more involved, because there are some technicalities in how you represent this branch cuts as finite coupling. I just wanted to add another thing is that usually this P characterize your quasi-momenta on your S5, while your Q characterize some classical quasi-momenta on your ADS5 background. Okay, so this is more or less what I wanted to say. So the point is that we have a tool to control this wrapping effects for the spectrum. The tool is this QSC. It works pretty well. You practically have control over all the possible operators that you can think of, and it gives you anyway a set of functions that should that encode all these finite size contributions. So this QI and this this piece. You can also take some limits for which you study operator, which are very, very large, and then this Q will transform and it will become some sort of a different Q that has. Okay, anyway, this doesn't matter, but you can take different limit of these P and Q functions, and this will counterpose to some specific limit of your spin chain. So you can take this asymptotic limit for which you obtain different Q functions, and this represent your this kill all the possible wrapping effects. So you have also some way to check that what you have done is correct, because you knew how to solve this asymptotic length limit in a different way. Okay, let me go on and let me try and explain how we use integrability to construct structure constant. So structure constant are somehow associated with 3-point functions, and in what I need to do then, I need to practically contract my 3-point operator, which are again spin chains between themselves. And what I'm practically computing, if you have heard the talk of Charlotte, are overlaps between different spin chains. As this is in principle a very complicated problem, what we would like to do is that we would like to simplify it by choosing two operators which are protected. So these are two vacuums, so two simple spin chains, and one which is not protected. And I will specialize to a particular operator which is of great interest for the QFT community, which is called the Konishi, but for now we can leave it generic. So the setup that we want to analyze for the structure constant is not the full, as we have done for the anomalous dimension. So we need to specialize to a particular subset of structure constant where we have more control. Otherwise, the problem is too difficult. So there are still some steps to be done in understanding how to work with 3 non-protected operators. Anyway, so the idea is fundamentally this, and let me introduce the main protagonist of what we care about. It's this hexagon. So what is an hexagon? Well, this is more or less a self-definition. It's a building block for correlation function in general. But the idea is literally you try to study this 3-point function, so as this pair of pens in the stringy picture where you have excitation only on one of the edges. And the idea is that I can always cut between these non-spin chain sides and obtain two hexagon-looking objects. I'll be more precise later, but this is more or less the pictorial idea, is that I can, by inserting some resolution of the identity between these edges, I can always construct a simpler object that it's a form factor. And what I need to do then, the complicated part is how can I generate this object, so this hexagon form factor, and how then I can sew it back. So how can I then glue all the edges back together to go back to the picture where I could generate the structural constant. So there are 2 steps. The first step has been solved by Benjamin and other collaborator, and you can construct this hexagon form factor to whatever loop, how many loop you want, is written in a very compact way. And they fixed it again, as it was done for the S matrix, by using the symmetry of the theory. So they could, using the symmetry, using form factor axiom, so Watson equation and other things you may be familiar with, they were able to build this building block. So the idea is, again, I have this single building block, and then I can sew different together to construct pans, so to construct more complicated geometries. And so the idea is then, okay, what I need to do if I want to compute structural constant, where I need to, first of all, understand how to plug in back the identity in here, and then I need also to understand how to construct these different hexagons with different particles inserted at different positions. As I mentioned, you need to do this sum over all these are called mirror channels. It's not too much important, but the idea is that at each order, or if you want, I will start with inserting 3 times the vacuum, then 1 particle here, 1 particle here, and so on and on and on until I've exhausted all the possible insertions. So this is in principle a very complicated sum to tame, and this is not what we're going to talk about. We're going to talk about some problems when you try to redefine, when you try to glue back together these 2 hexagon form factors. So,
sorry,
yeah.
Just these building blocks you use to reconstruct your object. What is it exactly in the language of spin chains?
I think I can show you later. It has different meanings. So it's usually one Godin, so it's a Godin norm, and then it's dressed by some factor depending where I put my mirror particles. So practically, it has some dynamical part, which is usually transfer matrices if you want, and then has a norm part, which is simply a Godin determinant. I don't know if this answers more or less your question. So the difference between the anomalous dimension and structural constant, and then in the structural constant from QFT point of view, you are inserting some dynamics. So things are it's connected to something that feels anyway to this 3-point function. So I have 3 operators interacting between themselves, and the 2-point function, which is the anomalous dimension, usually operator interacting with itself. So it has more, it needs to have more dynamical information if you want to construct the 3-point function. I don't know if I'm making too much sense to someone a bit outside of this picture, but the idea is that, in practice, is what I said. You have some norm, which is controlled by this Godin determinant, or could be also a Fredholm determinant, and then some transfer matrices that gives you how this object interact. So these are the 2 these are the 2 objects that appear. And as I said, you need to resum with different particles. And let me show you Exactly, this asymptotic contribution. So this is the first thing that one would like to study, which is exactly when I insert 3 vacuums in my cutted edges. So I have no particle here, no particle here, no particle here, and nothing here. I just have the excitation coming from the spin chain. And this is exactly, as I was saying, this is a Godin determinant, so it's a norm multiplied by a sum over all the possible ways that I can split the Bethe roots between the 2 different hexagons. So this is it's just like a combinatorial problem. Of course, all this sum of partition of Bethe roots depend on some of this hexagon form factor H, which is how which depends on the Bethe root. So how I split the Bethe roots, I will get different product of this H form factor. And an interesting thing that was noticed in the first time is that, of course, if I make this if I make the interaction between, so let me go back to this picture, which makes it a bit more clear. The more interactions, so the more fields I have here, and the more fields I have here, or the more spin chain sites that I have here, the more this I will have contraction between this and the spin chain that I want to study. And the more of this construction, the more difficult or the more energy it will be required by a particle to interact with all of them. So this is some sort of damping factor which depends on the length or how many contractions I have between these 2 spin chains. And if I chose my spin chain to be asymptotically big, I can always dump this factor. And the idea is that this is the only contribution that I have. So in some sort of sense, as we had for the anomalous dimension, if we use some asymptotically large spin chains, we have everything under control. So we can write this and this will be correct. Okay, what happens if I don't have asymptotically large bridges? Well, the idea now is that I specialize to some particular operator, which I call the lowest. It's practically, if you know, we're in the SL2 sector. So this is something which has length 2 spin 2. So it's, as I said before, it's something that has a trace of double derivative with z square. And I can have this, for example, at 2 loops. So if I don't want to study only the asymptotic, the first thing that I can have and is mirror particle in this. So when I resolve this identity, I don't only have like the vacuum, I also have the 1 particle state. Then at the next suborder, I will have this, the 2 adjacent ones, we come with the same order. And then the more I address this, the more complicated objects I need to have. So just to show a bit of flavor, which maybe can answer your question, this is the form of this contribution. So you have the asymptotic contribution, which is as before the Godin, and then we have a transfer matrix in the anti-symmetric representation with the V in this case is the rapidity of this mirror magnon, and then this is addressed by some hexagon form factor with computed at some, which is dependent on the Bethe roots of the state that I care about, and then there is this measure which is something intrinsic of the hexagon, and all of this, it's just a very complicated way of saying that this is 36 zeta 3 for our lowest state. So at the end, I know that my end final result has to be, if I expand in perturbation theory, it has to be some zeta values. So this is what I expect. So it cannot be anything else. But this is more or less the idea. You know how to write all these objects. You know how to do all of this. So in principle, everything is solved. Well, everything is solved up to you arrive at a high enough order where you get 2 mirror particles that live on 2 different edges. And you see, since I'm always constructing things that have integration, I have a region where if this U and V have the same rapidity, so where U and V, I get some wrapping correction. So I get some infinity arising, and the more I go over, the more terms I produce in this series that for my regluing, the more of these terms I will get. So this I will still get 1 wrapping, which and then 1 magnon here. In here I will get something which we can call the triple wrapping. So I have 3 magnons that can have all the same rapidity, and at 6 loops I also get the double wrapping effect. So is it more or less clear what's happening? So the idea is that we have an object that we can control really well, which is this hexagon form factor. And then if we want to reconstruct structure constant, which is the important building block for our CFT, we need to glue it back together. This gluing is, as I said, the resolution of the identity. And to resolve this, we need to, at each order, write this infinite sum and infinite number of integrals that represent the insertion of single or multi-particle magnons on each of these mirror edges. Okay, and the problem that arises if one tries to do this already at low loops is that you get these infinities. So you get your expansion gets infested with all these objects that are 0, because there is a region where the two magnon rapidities can be the same, and then you get infinity arising. This is clearly bad, but yeah, you don't want to throw all this hexagon formalism away, because I mean it matches perturbative data, so there is some truth in what we're trying to do. So you need to uncover some renormalization procedure to get rid of these poles, and this is exactly the scope of our work. So the first thing that one needs to try and understand is how this divergences arise. Well, we can, as we have done here, so this integrand can be actually rewritten in a more compact form, if because also it factorizes. But anyway, you can write it in a more compact form. Well, this WG, WB, and WRED are the three different contribution to this, the integrand that you need to construct for the different magnons. So you have practically, before integrating and before summing, this is the integrand that you want to have, and then you can expand to, if you want to do perturbation theory, you can expand it to whatever order you want, and then you will construct all the other contribution that I was writing before. Then you will need to do this integration. And the problem is exactly in this propagator under here, which more or less scale as UG minus UR square, and this gives you a pole. So this gives you something that is divergent, and you need to cure it. So the idea, which is very complicated, and I'll try to skip and just present a bit a feeling for it. It's the fact that you want to this integration, you want to deform the contour of integration by adding some I0 procedure, as you can do. So you shift a bit the two contours, and by doing so, you're able to construct something which is actually finite, and then you have some contact term which is one folded less, so you need to add, and you need to modify your integrand, but the idea is that you need to add some delta function that studies exactly this, what happens when U and G are the same, and you can modify your integrand accordingly, and then you have this localized one-fold term. So this is an integration less, so this is some delta function at U, the two rapidities being the same, and with these two, you're able to construct something which is finite and gives the correct prescription, so matches perturbative data. And this was done first in a more heuristic way, but then with Benjamin and Arthur, we derived a more proper way of doing it. It's a bit complicated. It requires a lot of, a bit of guessing and some form factor manipulations. I can more or less say, I mean, the idea is briefly that you cut only one edge, and then you construct some sort of 2-point function with another operator in the middle, and then you try and study how this corrects your hexagon. Okay, so the main point that I wanted to go through is that divergences arise. We have a method to construct objects which are finite, and we have some regularization procedure. Now, let me try and show you exactly what happens. So if I now want to renormalize my asymptotics, we see that actually this wrapping effect is practically a renormalization term. So it's another term that corrects this value. And of course, the more wrapping I have, the more corrections I need to, I can add. So the idea is now that I want to maintain the same structure of this object. What I want to do is that I want to modify what I call the different integrands W. And I can do it by practically studying this wrapping effects, so these contact terms, as I said, renormalization, so correction to the same hexagon without, for example, in this case, any other particle. So this will renormalize this, while this object, since I have one insertion here, will renormalize this hexagon. Okay. As I was mentioning at the beginning, we had some problems at 5 loops because we were getting some discrepancy between what we were expecting from the hexagon formalism and from perturbative data. So there was this extra piece that we could not account for. But now this double fold integral, because now in this case we have 2 delta functions. This is part of, in some sort of way, is like there are in the bottom bridge there are 2 waves. So there are 2 contributions I need to care of. One contribution which has some positive energy, and one contribution which has some negative energy, and it was dumped and it was not possible to see it until 5 loops. Okay, so to summarize a bit what I've said up to now is that this divergent, bad, regularize, and then understand how in this regularization your fundamental objects, which are practically the single magnon insertions or the multi-magnon insertion, get corrected by wrapping terms. And we know how to handle wrapping terms because we have this regularization procedure that works well at each order. Okay, so all of this to say that now we can practically rewrite our integral for our 3-point function as some sort of in a completely finite way. So now all these objects are well defined, everything works very fine. As I was saying, this W now are addressed. So practically I have inserted, as if before we had transfer matrices, now we have this special called dress transfer matrices, because they need, of course, to account for these extra wrapping effects that we have. So anyway, they can be determined in terms of y functions, which are, and again, some non-perturbative building blocks that was also used for this for the spectrum. But I mean, the fundamental idea is that the structure of the integron was correct. What was missing was a bit understanding this divergences. Once you have understand the divergences, you have control over all the possible effects, and you can write something that makes sense and is finite. And this is the object that you can try and hope to extend to all possible wrapping effects, which is what we have done for this particular single magnon excitation in the bottom bridge and for all the other ones, but especially for this one, we have some integrand. So in this case, we can, by solving this equation and plugging in some clever analytic continuation, you can write this bottom integrand, again, renormalized, so everything that is finite, as a combination of Q functions. So this is a very, at least for me, nice result, because now this is not only the single magnon in the bottom bridge that I was discussing before, is the single magnon in the bottom bridge plus all the possible wrapping plus all the possible wrapping that I can build on top of this. So this is a finite object. I then need to know how the Q function are. I can compute them perturbatively. I can go to which loop order I want, but this is the correct object to look at. So it's not the one that I was having before, is this. So this is the renormalized integrand, and this needs to be integrated over V, and then needs to be sum over all the possible bound state. But this is not complicated, it's just a computational problem. And if I add more of this mirror magnon, the idea is that you would have multiple copies of this QQ integrand, and then of course they will interact between themselves. So the structure will be complicated, but in some sort of sense, we have all the building blocks to construct all the multi-magnon bottom bridge and adjacent and non-adjacent. And also, yeah, we have some other insight on what this normalization factor, which is in the previous was this Godin part, needs to be modified to actually take into account this where is it, this wrapping here, this wrapping correction. So this cannot be a go down anymore. It needs to be something that has to account for this wrapping. Very good. So we have this. We have control over it. By using this QSC, we can construct this Q function. We can construct this integron, and then we can integrate it and sum it. And this is exactly what we have done. And for this particular operator that is called Konishi, where we have, as I said before, two vacuums, so two z square and a state which has two insertions. So this double derivative are this two spin up, if you want, in a sea of spin down, or two spin down in a sea of spin up. We were able to compute this QQ function. We were able to compute the integrand, and from perturbation theory, we had the result up to 5 loops, and we were able to match WB onto the 5-loop result. So we believe that what we have written should make sense, and I mean we have this very non-trivial test. So to summarize, hopefully, what we have done. So we have interpreted this triple wrapping, so this extra piece that was coming up at 5 loops, as a new fundamental object for this bottom bridge. So this retarded second wave that we could not see from the canonical hexagon construction. As I mentioned, the QSC is a very good object to look at for building wrapping cautious term, and we were able to construct this integrand, which is this for this bottom bridge, and we also have it for the adjacent and for this normalization factor in such a way that is actually it works. I mean, it works. It works up to 5 loops, but we believe that it should work also for higher loops. And also, since this QSC pieces allow for a strong coupling, so a classical limit, we're also able to check in that regime that this conjecture will make sense with some classical string results. And as I said, these same ideas were applied to this adjacent bridge, which are this green and red. And we were also in there, we had some matching with known semi-classical data. So the bottom line of all of this very contorted thing is that we hope to have unveiled a new piece, or a new, nicer way to have under control this wrapping effects, and we've hopefully written something that is nice and efficient way of constructing at least structure constant for this particular non-BPS, BPS combination. Perturbatively for sure, non-perturbatively maybe not, but at least it's a first step into trying to solve this structure constant for for non-perturbative. Anyway, this is it. Thank you.
Other questions?
Could you now with that compute something like 6 loops, 7 loops, 8 loops, 9 loops, or I mean just to have some additional data? You could probably. Yeah,
I mean, I can. I mean, there is a perturbative way of constructing the Q function, which is, I mean, you have some people wrote some very nice code that can construct the P, and then you can translate to the Qs, and then you can expand the Qs. And the space of function, I did not explain it, but it's very trivial. So you take this residue, so you solve this integral by residues. This will give you some harmonic sums and nested harmonic sums, and then you just, it's like you compute them at infinity. So you'll get MZVs, Zs, and then it's just some algebra. So getting the result is not a complicated way, but the interesting piece will be to match it again perturbative. But doing 5 loops took us like a year. Doing 6 is probably right now impossible. So I don't. Yeah, we're at a moment where we can make some prediction, as you said, and then it would be nice if someone could check them by some other computation. I don't know how, but maybe some.
Or maybe also some CFT methods could.
Yeah, there could be.
Do something. I don't know.
Yeah, the problem with CFT is that. Yeah, they care more about double trace because they do this strong coupling, right? So at least the CFT that I know of is usually in this supergravity regime, so it's a bit detached from this picture. But it could be that there is some other clever idea as to how how to put some constraints of this. But yeah, our strong coupling results are a match with what is known from the literature. So this is also a non-trivial test. Yeah.
So what Alessandro explained is that once we have the formula written in terms of Q function, so if we want to expand to a certain order, we can just ask people who develop this solver to solve for the Q function perturbatively and get the answer to very high order. But the additional difficulty that we have for structure constants is that at the end we need to integrate over all rapidities and sum over all bound state, because these are inclusive sum over all the phase space of, and that part can actually be relatively complicated. So at the moment we don't have technology that make this step, straightforward. So at each loop order we have some difficulties, and so I would not claim we can do 6 or 7 loop in as easily as.
At least, I mean, for this probably yes, because it's the simplest one. But I agree, the adjacent is probably not possible. So yeah, well, this we could probably do, but the rest is too complicated.
So is the 3 Magnon interaction divergent? The contact term is divergent?
No, at the end. So of course, so this, where is it? I don't have. Yeah, this. So in this, after you do this renormalization procedure, you will get a one-fold contact term. So this, where these two have the same rapidity, and then you will get a threefold contact term, which is this. But they're all finite. I mean, you have taken care of all this infinity. So this is a finite effect, and this is exactly why you need to use Q function and you cannot use transfer matrices anymore. I mean, you need to dress your, both this and this object need to come into play at 5 loops to have the correct answer. Because if you don't, and if you just use the normal one and hope that, don't dress it with these extra 2 terms, you get only this asymptotic, but it's not the correct answer. I don't know if it was precise enough. But,
so somehow this term simplifies the answer.
Yeah.
The extra term simplifies the answer, because if you just compute the
in some sort of sense, yeah. I mean, I don't know what you mean by simplified answer. It's nicer to look at. I mean, it's just a product of the Q functions, and then it's I don't know. It's something that has more sense also non-perturbatively, and again for this wrapping. So yeah, this object was important, and also the regularization was important. How to understand how this works, but yeah. Maybe he can know better.
And I mean, it's like it's usual 3 with n equals 4. Yeah. So the sum is nicer than the part. So when you sum everything else, everything, you get something that is nicer than.
When we were trying to look at the just the 2 Magnon contact terms, they were not very simple. Yeah. So yeah.
When we did the first time the computation, not using the QSC, there was indeed a magic cancellation between something here and something here that actually simplified the answer. So yeah, in that sense, this helped. Is that once you go to this QSC, it's even simpler, because also you don't get a 2 integral, you just get 1. So 1 is done automatically for you, and it's even more simple than trying to do this regularization. But yeah, getting there was not easy. I mean. Yeah. Yeah. Good question. I think it's not, you don't have the form factor either. It's not, I mean, I think, I'm not an expert. I think that there is a problem in constructing. You don't have enough symmetry to fix. In n equal 4, you have enough symmetry. You have this SU2, 2. Yeah, anyway, you have enough symmetry to fix everything. In the IBGM, you don't. So you cannot even say what H is. So, no. No. Yeah.
If there are no more questions, then let's thank Alessandro again.